Hello students, in previous lecture we had discussed about the machine design philosophy, general procedure of design, steps of design of machine elements and the general consideration during the machine design. Today we are going to learn about the stress strain diagram for the both material, that is ductile and brittle material, and one numerical on the tensile test. So let us start with the stress strain diagram. Now in this video we will discuss about the stress strain diagram for both material, ductile and brittle. So one by one we will discuss stress strain diagram for ductile and brittle. So for the stress strain diagram drawn by conducting the tensile test on the standard specimen of particular material and noting the corresponding values of load and elongation until the specimen fractures. Now for conducting this tensile test, we have suppose a specimen . This is the standard specimen and it is loaded under the machine. With diameter, initial diameter is D and length is D1 and length is L1 suppose. Okay, and we will conduct the tensile test on this specimen. This is the machine and this specimen is placed under the machine for the tensile test. Now the load is applied and measured by testing. Okay, now how to calculate stress? For the stress we required load and the cross section area. So the stress is determined by the load value by original cross section area. Now we can calculate the area of this specimen, that is pi by 4 d1 square, and the strain, that is changing in the dimension upon the original dimension. So the elongation, because by loading this specimen the elongation will occur in the specimen, and the elongation is measured by determining the amount of the two reference point. So here we will put two reference point and the distance between these two reference point is known as the gauge length. So here the gauge length is suppose L1. The gauge length is suppose L1, and the value of this stress and strain, corresponding strain, are used to draw the stress strain diagram of the material tested. Okay, so let us try to draw the pattern of the stress strain diagram for the first ductile material. So before starting this stress strain diagram, we should know what is ductile or what is ductile material. So the ductile material means the material which can drawn into the thin wire when it is loaded. So ductile material. For example, mild steel, copper, aluminum, such type of materials are ductile material. And in the second part we will discuss the stress strain diagram for the brittle material. So brittle material examples are ceramic, cast iron, etc. So to draw this stress strain diagram, we will put stress on y-axis and strain on x-axis. Stress, it is denoted by sigma, and strain, okay. Now in the stress strain diagram, initially the load is applied and we will observe that the stress is directly proportional to strain. So from O to A, the stress directly proportional to strain. Okay, so O to A is a straight line, that is stress is directly proportional to strain. That means it obeys the Hooke's law. What Hooke's law says? The stress directly proportional to strain within the elastic limit. This is the Hooke's law. So this A point O is known as the proportional limit. So A point is the proportional limit. Now from A point, if we increase the load, this curve is slightly deviate from the A point up to the B point. So B point is known as the elastic limit. That means if the load is increased between A and B, the body will regain its original shape and size when the load is removed. That means up to B point, this material possesses elasticity. So this region is known as elastic region. So this pink colored is elastic region. After point B, if the load is increased, the body undergoes the permanent deformation. So from B, the plastic region will start. So this will continue up to the point C, and hence the C is known as the plastic limit. But here we will observe the yield stressing at point C and D. So in the stress strain diagram, if the load is increased beyond point B, the body loses its elasticity. That means the plastic stress will reach. Plastic means on the removal of load, the material will not get its original or recover its original shape and size. So this point C is known as the upper yield point. Now further addition of small load drops the stress strain diagram to the point D. Point D. Now this C and D are very closer to each other. As soon as the yield starts, and this point D is called as the lower yield point. So the stresses corresponding to these C and D points are called as the yield stresses. So in the ductile material we observe yield stress. If the further we increase the load beyond point D, there is increase in the stress up to the point E. Now this graph will reaches to the maximum value of the stress point E. So this is the ultimate stress of this curve, and that is known as the ultimate stress. So simultaneously the strain increases, which is followed by decreasing the cross section. Now this component area will reduce due to the elongation. So due to elongation, the cross section area is decreased. Now this is the ultimate tensile stress. Now when the specimen reaches to the ultimate stress, the neck formation, this is our specimen, and this is the neck formation. So neck is formed. So the neck formation takes place along with the further decreases in the cross section area of the specimen. Due to the reducing the cross section area, the neck is formed. At this point, the stress required to break away the specimen is less than the maximum stress. Now this is the maximum stress. Now for breaking this material required very less stress. So at EF point the material will break, and the corresponding stress is known as the breaking stress. So this behavior of the stress strain diagram, the stress strain curve, will observe in the ductile material during the tensile test. Now similarly, if we use the brittle material specimen and conduct the tensile test on the brittle material, we observe the curve like this. So similarly, we will take stress on y-axis, strain on x-axis, and draw the stress strain diagram for the brittle material. Now in the brittle material also there is a stress directly proportional to strain up to the point A. So here we will take the specimen of the cast iron, and load is applied on the cast iron. So initially we will observe the stress directly proportional to strain from O to A, and this is known as the proportional limit. Now each such material elastic limit lies above the proportionality limit up to the point B. So after this elastic limit, the curve shows a permanent deformation. So here also elastic region up to the point B. So this pink colored is the elastic region, and beyond this elastic region we will observe the plastic region. Now from B we will observe the plastic region. So at this E or F, that is the ultimate stress or baking stress. So at ultimate stress, this brittle material or brittle material specimen will break. So in this brittle material we will not get the neck formation. So there is no intimation before failure of this brittle material. But in the ductile material we observe the neck formation and we get the intimation before the failure in the ductile material. This is the basic difference between the ductile and brittle material. In both diagram we can show this is the plastic region, so these both diagrams are always asked in the examination for 4 marks, and we have to mention each point. So A is the proportional limit, B is the elastic limit, C is the upper yield point, D is the lower yield point, E is the ultimate stress, F is the breaking stress. For the brittle material we will not observe the yield, so we will get directly ultimate tensile stress. So in the brittle material stress strain curve diagram, A is the proportional limit, B is the elastic, and F or E point is the breaking point or ultimate tensile stress. Now in the ductile material we observe the yield. Therefore this design of the ductile material is based on the yield stress, and the design of the brittle material based on the ultimate tensile stress. These are the basic difference between these two diagram, ductile material stress strain diagram and brittle material stress strain diagram. So be careful for during the design of the ductile and brittle material. So for ductile material we will take the yield stress for the design, and for brittle material we will take the ultimate tensile stress for the design. Now here we have taken one example based on the tensile test. So in the numerical, a mild steel of rod 12 mm diameter was tested for the tensile strength with a gauge length of 600 mm. Gauge length means the distance between two reference points on the specimen. So initial length is 600 mm and initial diameter of the specimen is 12 mm. Now following observations were recorded after the test. Final length 800 mm, that means the component is elongated by 200 mm. Final diameter is 7 mm. So the diameter will reduced. So final diameter is 7 mm. Yield load is 4 kilonewton and ultimate load is 6 kilonewton. We have to calculate yield stress, ultimate stress, then percentage reduction in area and percentage elongation. So the given data is initial dimensions and the dimensions after the testing done. So try to solve this example. So here given data is initial diameter is D1 equal to 12 mm. Then initial length, that is gauge length, that is L1 equal to 600 mm. And final length, that is L2 equal to 800 mm. Final diameter is 7 mm, that is D2, 7 mm. Yield load that is WYT is equal to 4 kilonewton. 4 kilonewton means 4 into 10 raised to 3 Newton. Then ultimate load equal to WUT is equal to 6 kilonewton, and that is 6 into 10 raised to 3 Newton. Now we required cross section area for calculating the stress. So first of all we will calculate the area for both initial and final, and we have to find yield stress. Second one is ultimate tensile stress. Then third one is percentage reduction in area, and fourth one is percentage elongation. So first of all we will calculate the original area and final area of the specimen. So original area of specimen is A1, that is pi by 4 D1 square. So it is pi by 4 into, now diameter is 12 mm initially, so 12 square. So by calculating we'll get 12 square into pi divided by 4, so we'll get 113.09 area in mm square. Okay, now final area that is A2. Similarly we can calculate pi by 4 D2 square, so pi by 4 into 7 square, so we'll get pi by 4 into 7 square, so it is 38.48 mm square. Okay, now we will calculate yield stress, ultimate tensile stress. So first is yield stress. Now for yield stress we required yield load upon cross section area. Now here we will take the original area for the cross sectional area. Okay, so yield stress is equal to WYT upon A1, initial or original area. So it is 4 into 10 raised to 3 upon A1 is 113.09. So we'll get 4 into 10 raised to 3 divided by 113.09. So it is 35.37 Newton per mm square. Okay, this is our first parameter. Second, we have to calculate ultimate tensile stress. So calculate ultimate tensile stress. So ultimate tensile stress. For that we will take ultimate tensile load. So ultimate tensile load upon cross section area. Here also we will take A1. So 6 into 10 raised to 3 upon 113.09. So 6 into 10 raised to 3 divided by 113.09 will get 53.05 Newton per mm square. Now we have to find out the percentage reduction in area. Percentage reduction in area. Percentage reduction in area. For that we require reduction upon the original. So here original area is more. So original area minus final area, and reduction in original area. So original area is at denominator. Original area. This is important. The difference upon original, because the reduction in original area. Therefore A1 minus A2 upon A1. So we'll get 113.09 minus 38.48 upon 113.09, and percentage means into 100. So into 100. So by calculating we'll get, now reduction is 113.09 minus 38.48 upon 113.09 into 100. So we'll get 65.97% reduction in area. Now we have to find out percentage elongation. Elongation means increase in the length. Elongation. So similarly, now final length is more. So the difference between the length upon the original length. So here the final length is more. So final length minus initial length or original length, initial length. You can write here the difference in the length upon original length. That is also okay. Initial length. So you have to find out the difference in the difference between the final length and initial length. So final length is 800 minus initial length is 600 upon initial length is 600. because elongation is on the initial length. So for percentage into 100, so it is 800 minus 600, 200, 200 upon 600 into 100. So 200 divided by 600 into 100. So we'll get 33.33% elongation in the specimen. So such type of simple numericals in the first chapter, and some numericals are asked in the examination based on this tensile test. So there are only 4 basic formulas in the tensile test: elongation and reduction in area calculation. So I hope that today's lecture everybody understood. If any doubt about this topic, please write your comments in the comment box, so I will discuss with you in the next lecture. Your difficulties will be solved in the next lecture. So if you like this video, please like, share in your friends, and study carefully